and hi everyone. Okay, I hope you guys are good wherever you are. Okay, so this is my first video for CHM 477 Introductory to Inorganic Chemistry. Okay, so alright, let's start with our lesson from 16 March. Okay, so for today we will be discussing about molecular orbital theory. Alright, so these are the presentation outline. Okay, first one is the types of molecular orbital. Second one is the homonuclear diatomic molecules. Okay, for the first and second we have covered these two during our last class. Okay, and then third one, heteronuclear diatomic molecules. Okay, this is what we will be discussing for today, and also the bond order. Okay, so last class we have stopped here. Alright, this is all about the differences of the relative molecular orbital energy levels for period 2 homonuclear diatomic molecules. Okay, so as you know, okay, as you can see from here, this is where we have the energy levels for oxygen, fluorine, and also neon. Okay, as you can see, this is where we have the without sp mixing, and this is where we have the with sp mixing. Okay, the main difference between these two is the arrangement of sigma and also pi at 2p level. Okay, here we have sigma 2p, pi 2p, pi star 2p, and also sigma star 2p. Okay, this is energy level diagram for oxygen, fluorine, and neon. While for this one, okay, where we have the sp mixing, okay, the pi 2p, sigma 2p, pi star 2p, and also sigma star 2p. Okay, other than that, okay, this is where we have large molecules, while this one we have small molecules. As I have said before this, okay, we have different arrangement at 2p levels, as you can see here, and also here. Okay, alright. So the general energy order, okay, for these two is actually sigma 2p, pi 2p, pi star 2p, and also sigma star 2p. And then, right, next is where you need to draw the diagrams of all these orbitals, okay, as you can see from here. Okay, and you need to know from this diagram, you need to know two terms. Okay, here is first homo and also LUMO. Okay, homo and also LUMO. So what is homo and what is LUMO? Homo is the highest occupied molecular orbital, while for the LUMO is the lowest unoccupied molecular orbital. Right, so I will explain to you later about the homo and LUMO. Alright, so the first thing, alright, for this diagram, that you need to be able to draw, okay, the orbitals or the diagram for this one. Okay, what happened in the bonding and what happened in the anti-bonding. Okay, as you can see, sigma and also pi. Okay, here this is where we have the overlapping between end to end. Okay, hujung dengan hujung. And also when you have the pi, this is where you have the overlapping between side to side. Maksudnya tepi dengan tepi. Okay, right. So this is the energy level for oxygen, fluorine, and also neon. Alright, this is where they have without sp mixing. Second one is the diagram for energy levels for boron, carbon, and also nitrogen. Okay, the things that you need to do or you need to know here, as usual, how to draw, okay, the pi and also sigma, bonding and anti-bonding, and also you need to know what is homo and LUMO, right? Okay, and this one, they are having the sp mixing. Okay, so, right. We go to the bonding in the p block element. Okay, Alright, as you know, the higher the bond order, the greater the bond energy and the shorter the bond length. Okay, so other than HOMO and LUMO, you need to know another two terms here. Okay, paramagnetic and also diamagnetic or diamagnetic. Okay, what is paramagnetic? Paramagnetic is where you find an orbital without unpaired electron. Okay, with unpaired electron. So they are actually attracted to the magnetic field. Okay, while for the diamagnetic, this is where you find an orbital with paired electron. Okay, and they are unaffected by the magnetic field. Okay, how to determine the paramagnetic, the diamagnetic, the HOMO and also the LUMO. Okay, so these four things that you need to know. Okay, alright, so let's say I have an example of this figure 11.21. Okay, with SP mixing and also without SP mixing. First one. Okay, so what do you still remember about para and also diamagnetic? Okay, para with unpaired electron while diamagnetic is with paired electron. Okay, so for example, let's see here. Let's say we have the B2 here. Okay, the B2 here. Okay, so where B2, is it paramagnetic or diamagnetic compounds? Okay, alright, so for the B2, okay, as you can see at the pi 2p, okay, there is two unpaired electrons. So when you have two unpaired electrons, the B2 can be considered as paramagnetic. Okay, and then other than that, okay, let's say we have the example for C2. Okay, so do you see any unpaired electron? No, right? So when you don't have any unpaired electron, this C2 can be considered as diamagnetic compound or diamagnetic molecules. Okay, another examples. Okay, let's see. Okay, let's say we have here is O2. Okay, you can see here we have two unpaired electron at pi star 2p. So this O2 is actually a paramagnetic molecule. Okay, other than that, you can see this is neon 2. Okay, no unpaired electron at all, but the bond order is 0. So what does 0 mean here? Okay, so it means that the Ne2 does not exist. Okay, other than that, alright, we have covered the paramagnetic and also diamagnetic. Okay, you need to know another two terms, homonuclear. You need to know two terms. Okay, HOMO and also LUMO. Alright. So how to determine HOMO and also LUMO? Okay, HOMO is the highest occupied molecular orbital. Alright, so as you can see, for example, let's say we have this nitrogen 2. So where is actually LUMO or HOMO located? Okay, so the answer is for nitrogen 2, HOMO highest occupied molecular orbital. So you need to find, okay, electron at the highest energy level. So for the N2, the HOMO is the sigma 2p, and while for the LUMO, lowest unoccupied molecular orbital with 0 electron is the pi star 2p here. This is the LUMO while this is the HOMO. Okay, let's say we have fluorine, okay, F2. So where is the HOMO, highest occupied molecular orbital? The HOMO for F2 or fluorine here is the pi star 2p, while for the LUMO, lowest unoccupied molecular orbital with no electron at all is sigma star 2p here. Okay, alright, so please guys, okay, when you see the valence electron configuration for the molecular orbital theory, okay, so you need to write down it's like this. Okay, you need to list down all the molecular orbital theory from the bottom to the highest. Okay, from bottom to top. Alright, based on their energy level. Okay, from here to here. Okay, so here as you can see, the difference between sp mixing and without sp mixing is actually here. Okay, the arrangement of sigma and also pi to p, right here. Okay, and then so this is sample problem for nitrogen and nitrogen 2 plus, and then we have, okay, here the bond order for nitrogen N2 and also N2 plus. Okay, as you can see, the bond order for nitrogen is 3, while the nitrogen 2 plus is 2.5. Okay, so other than that, we have oxygen O2 and also O2 plus. Okay, here with the bond order of 2 here and also 2.5. Okay, here you can see we have different bond energies. Why? Okay, as you know, the larger the number of bond order, okay, what happened to the bond energy? It also will become higher. Okay, right, it same goes to here O2 plus. Okay, the larger the bond energy, the larger the number of the bond or order. Alright, so this is can we have here? Okay, this is where we have the bonding of electron loss, while this one is the anti-bonding electron loss. Okay, alright. Okay, so what is the HOMO for N2 plus and LUMO for these molecules? Okay, the HOMO will be sigma to P, while the LUMO will be pi star to P. Okay, let's say here for the O2 plus, okay, an example for this one. Okay, this is the HOMO. Okay, at least you need to have one electron, okay, in order to determine the HOMO. Okay, and the LUMO for the O2 plus is the sigma star to P. Okay, sigma star to P here. So guys, this is the table for 10.5. Okay, this is similar on what we have discussed before this. Okay, okay, as you can see, lithium Li2 is a diamagnetic because we have paired electron. Okay, and then oxygen, okay, O2 is a paramagnetic molecule, okay, because we have 2 unpaired electron here. Okay, so this one for this table you can read by yourself. Okay, this is just an example or summary. Okay, alright, so what happened for oxygen? Okay, alright, from the Lewis diagram, okay, as you can see from here, okay, it shows that oxygen is a diamagnetic compound, right? Because as you can see, we have 4 lone pairs, okay, around surrounding the 2 oxygen atoms, okay, with double bond. Okay, so the bond order for oxygen is 2. Okay, alright, but from the MO or molecular orbital, it shows that actually oxygen has 2 electron unpaired or 2 here. Okay, alright, so which one is true? Okay, is it oxygen is paramagnetic or diamagnetic compound? Okay, right, so okay, researchers have done an experiment, okay, where as you can see from here, okay, liquid oxygen is passed through the magnet here, okay. So what happened? This oxygen attracted to the magnet. Okay, alright, so when this oxygen is attracted to magnet, okay, oxygen is a paramagnetic compound. Okay, alright, so okay, if you compare Lewis diagram with the molecular orbital, which one is more accurate? Okay, the answer is the molecular orbital. Alright, theory. Why? Because from here, this oxygen show you that oxygen has 2 unpaired electron, while for the Lewis diagram, it shows you that oxygen is a diamagnetic. Okay, alright.